Welcome to the Chapter 5.6a lesson video. Today we're going to be talking about growth and decay. And this is kind of one of those sections that applies everything that we've been talking about into something that's applicable to really real world type scenarios here. So as we get into this, it may be a little tricky at times. There's a bit of word problems and stuff like that involved and a couple formulas. So I would encourage you to make sure you take really good notes, to pay close attention, to write this stuff down, as it'll be really helpful as you start doing these problems. Breaking down the problems, annotating the problems is also a really helpful thing as you get started. All right. So let's go ahead and talk about these items here. Exponential growth and decay is the increase or decrease of an initial population by a value that is found to be repeatedly multiplied over and over and over and over. All right, so in previous classes, you might have talked about linear growth and decay. We might have talked about quadratic, but we're going to talk about exponential. And we've been graphing these, so you know it looks kind of like this. It starts out rather slow, and then as time goes on, it picks up, goes faster and faster and faster and faster. And this type of growth applies to a lot of different situations. Fiscally, like to money and economics, it's a really common occurrence. Biologically, to things like cell growth, bacteria growth, virus spread, that's something a little topical, and other things like chemistry, like radioactive decay, and stuff like that, all have this exponential growth involved. So we're going to do a couple of problems. I think we do 4 example problems here. We'll learn a couple formulas and how to use them, but let's go ahead and get started. So the way I look at these is we talk about this. So we have 4 different pieces that we're really working with, and it kind of gets broken down a little bit more in a second. But we have, we'll start on the top right here. We have t, this is time. Okay, so when you see t in your equation, that's your time. R is your rate of growth. Rate of growth. It's usually represented as something like a percent or something like that. Now you got to know how to change percents to decimal. It's something hopefully that we're all familiar with. P is usually called principal. All right, now principal is kind of a fancy word. Another way you can refer this is your initial value. This is your starting value, your initial value, and then A, this is your final value, your answer, in other words. All right. So P is your initial, R is your rate, T is your time, and then A ends up being our resulting answer here. So, all right, let's just do a sample problem of an exponential growth problem. It says a 200-foot length of rope is constantly cut in half. Write an equation to model the situation, and then find the length after 10 cuts. All right, so let's go ahead and talk about this one. So our formula will look something like this. We'll say A equals, our initial amount is 200 feet, 200 feet. So I'll go ahead, what I like to do a lot of times is annotate what the different things are in the equation. So like kind of label them like that. All right, and then it says it constantly gets cut in half. Yeah, half, that's our R in this case, our rate. Now, in this case, we can represent it as a decimal or a fraction, doesn't really matter. I'm gonna use a fraction just because that's how my brain thinks of 1/2. And then it gets constantly cut in half over and over and over. The first thing this asks us to do is to write an equation. So we'll leave t as the missing variable because we can cut it 1 time, 2 times, 3 times, 4 times, and this will be our equation that models this situation. So the number of cuts is represented by the number of times 200 is multiplied by 1/2. All right, then it asks us, so that was part 1 here, then it asks us what happens after 10 cuts. So this is our t for this scenario. So we'll go ahead and say A equals 200 times 1/2 t. Now you're probably going to want a calculator for a lot of these problems. T, not t, 10. 10 is t because they told us that it's 10 cuts. So you're probably going to want a calculator for a lot of these problems. It's going to be really helpful. If you don't have a calculator, remember you can always use Desmos. But yeah, so we'll go ahead and plug that into our calculator. We'll say 200 times 1/2 to the 10th power. And you get that the new length of the rope is 0.195 feet. All right, so it was a 200-foot rope. You multiplied by 1/2 over and over and over. So you go 200, then 100, then 50, then 25, then 12.5. You keep cutting in half over and over and over. After 10 cuts, you now only have 0.195 feet of rope left. Okay, so good example of an exponential change. Every time it gets smaller and smaller and smaller by half, and that is exponential growth, multiplying by 1/2 over and over and over. All right. So now more specifically, let's talk about growth and decay when we're given a percent. So that time we were given half, kind of a nice easy number to work with, cut in half, cut in half, cut in half. Now, when we talk about growth and decay, oftentimes we're going to give a percent. We'll say it grows by 3% or 4% or 2.7%, or it decays by 7%, or decays by 20%, something like that. And what you have to do, first of all, is you have to change that percent to a decimal. Now, if you don't remember how to do that, if I say something like 20%, what you do is you take the decimal place from right here and you move it over 2 spots. So 20% would be 0.20 as a decimal. Something you gotta be careful of is something like 7% isn't 0.7. 7%, remember you move it 2 times, is 0.07. So be really careful when you're changing these percents to decimal. It's kind of a big deal. All right, and here's how we write our formula. So we still have the same factors, the same playing pieces. This is going to be our final value. P is still our initial value, our principal. R is our rate that we are just talking about. So this is our rate as a percent. And T is still our time. Now you'll notice we do something here. What we're doing here is we have 2 different formulas. If we are growing, we are taking 100% of what we had and adding the new percent. So you'll get something like 1.05, meaning you have the 1 plus the 0.05% that gets added each time. Decay works the other way. You have the 100% that was originally there, but then you subtract some percent. So it'd be 1 minus 0.05, which is 0.95. So you'll see that this number on the inside, if it's growing, the number on the inside here is always going to be, that number on the inside is always going to be bigger than 1. Whereas if we were decaying, that number is going to be less than 1. The number inside the parentheses, if we're growing, we add to the 1, so it gets bigger, so you add your percent to the 1. If it's decaying, then it's going to be less than 1. All right, let's go ahead and read our example problem here and see if we can figure out what the different stuff is. It says, Alvin put $500 in an account with 10% annual interest. Man, that's good interest. That doesn't normally happen in the real world. When his son is born, how many years will it take his son to have $5,000 in his account? So let's label the different things that it's giving us right off the bat. So I'll go ahead and do that in purple here. So $500, this is our P, that's our initial amount. It says it is given to our account as 10%. All right, so this is our R, but we're gonna change it to be 0.10. So that way it's in a decimal. And it says how many years, that's our T, that's our question, that's what we don't know, will it be until his son has 5,000? So this one's interesting. This one gives us our A. Okay, so our A is this 5,000. So let's go ahead and write a formula and then solve for T, because that's what we're solving for this time. We're solving for our T. All right, so our formula looks like this. We have $5,000. Okay, that's what our final amount is going to be. We started with $500. Times 1 plus 0.1, and we're going to raise that to the T power. All right, so now we're going to solve this equation. We're solving for T, so it's going to require a little bit of our new math that we've been learning, a little bit of simplification, different stuff's going to happen. First thing I'm going to do is I'm going to divide this 500 right here over to the other side. I'm trying to get T by itself. I'm trying to solve for T, so I'm going to divide that 500 over to the other side. 5,000 divided by 500 leaves me with just 10. So I'll now have 10 equals 1 plus 0.1 is 1.1 to the t power. All right, and this is one of our equations that we learned how to solve in our previous lesson. So I'm going to go ahead and take the log of each side. So I have log of 10 equals t times the log of 1.1. And I'm going to divide that log of 1.1 over to the other side. So I'm going to get t equals the log of 10 over the log of 1.1. Now, this is my calculator ready answer, my calculator ready form. So I'll go ahead and I'm going to go log of 10 divided by log of 1.1. And I get an answer, a decimal approximation answer of approximately 24.16. All right, so let's talk about this. So we got our calculator ready answer, log 10 over log 1.1. That's our kind of exact answer. We calculated that to be 24.16, but let's talk about the context of this problem. This account gets annual interest. That means it gets interest at the end of each year. Well, so 24.16, that's not going to happen in the 24th year because there's a little bit more that needs to happen. So this will actually reach $5,000. It'll have at least $5,000 at the end of the 25th year. So 25 years is our final answer. Okay, so you kind of have to read the context here, right? This is our mathematical calculation, but in the real world, you don't get the interest at that 0.16 part here in this kind of problem. You don't get it till the end of the year. The real world might be actually a little bit different than that. We'll talk about it later. But you get it after the 24th year, so that means it's actually in the 25th year for your final answer. All right, we got 2 more practice problems to do, and then we will ask lots of questions and go over this more in class as well. All right, so it says an acidophilus culture contains 150 bacteria that doubles in population every hour. A says write a function that represents the bacteria population for every hour that passes. And then B says what is the number of bacteria after 12 hours, 16 hours, 24 hours. So this is more like our first problem here. So let's go ahead and do it. A says write an equation to model this situation. Okay, so the population, the final amount of bacteria is equal to the initial population. Let's go ahead and label that. That's our P right there. And it says it doubles every hour. So this is our R. This is our time. So doubles means times 2. So 200%. Okay, and then it says how many hours until this happens. So hours is our T in this case. So we have our initial population of 150 of these bacteria. Every hour they get multiplied by 2 for however many hours pass. So there's our part A there. Our part B here, we're going to go ahead and we're going to calculate it. How many bacteria are there after 12, 16, or 24 hours? So these numbers might get pretty big real quick. So let's go ahead and do 150 times 2 to the 12, 150 times 2 to the 16, and 150 times 2 to the 24. Let's go ahead and calculate each of those on our calculator and see what answer we get. So 150 times 2 to the 12, these are going to get pretty big pretty fast, is 61440. All right, so that's 614,400. Let's go ahead and change that exponent to be a 16 instead. We get 9830400. All right, so now we have 9 million. So after just 4 more hours, we're now up to 9 million from 600,000. And let's see what happens after 24 whole hours, a whole day. How many bacteria are left? Wow, this number got real big real fast. We got 251,658,2400. All right, so going from just 16 hours to 24 hours, we now have 2,516,582,400. So you can see this exponential amount. It's growing faster and faster and faster and faster and faster and faster. Each hour that passes, that doubling amount doubles and doubles and doubles on top of itself. So what's happening is before you doubled, but then you now have double the amount to double. And so it just grows really, really fast. And that's why our graphs of exponentials look like this, is they just shoot up really fast because there is so much growth so fast. Okay, one more problem. All right, one more example. It says a city population, which was initially 15,500, is dropping by 3% a year. How many years until the population falls below 8,000? So we want to be below 8,000. All right, so that's our final amount, 8,000. Our initial amount was 15,500. All right, so that's our A. That's our P, and our R is 3 here. And so this is a little bit different one. This is the one where we have to use the percent. So we go 1 minus 0.03, and we're trying to figure out how much time this takes. All right, so we'll do some little calculations here. So 8,000 divided by 15,500. So we'll divide the 15,500. We'll get 8,000 over 15,500. That doesn't simplify super nicely, but we'll deal with it in a second. 1 minus 0.03, that is 0.97 to the t. All right, so that left side, we can simplify it a little bit if we want to make it look a little nicer and be a little less pain of a write. We can cross off these zeros at least, so 2 zeros from top, 2 zeros from bottom, a little less to write, so we just write 80 over 155 instead, but I would leave it like that. Don't change it to a decimal. You'll get some rounding error somewhere. Let's keep going. So we have 80 over 155. I'm going to take the log of each side, so I go log of that equals t times the log of 0.97. So the reason I did that was so I can move my t down. I'm going to divide that log of 0.97 over, so I will get t equals the log of 80 over 155 over the log of 0.97. And so I'll plug that in my calculator, get a decimal approximation. So I will go log of 80 over 155, and then divide that by the log of 0.97, and I will get approximately 21.71 years. And now in this context, this one's a little tricky, right? We have to kind of think about it logically. How many years will it take for the population to fall below 8,000? Well, at the 21st year, it wasn't, but at the 22nd year, it was. But are people all moving out on New Year's Day? No, probably not. But let's go ahead and read it. At the start of the 22nd year, the population will be below 8,000. And that's the kind of context we should read this in. Okay, now, realistically, are they all moving out New Year's Day? No, so it's somewhere between the 21st and the 22nd year, but we just say at the 22nd year is when this population. So let's assume they take the city's population on New Year's Day every year or something like that. Okay. All right, so with that, you should have enough to be able to get started on the assignment. If you have any questions, please feel free to reach out. Otherwise, I'll see you in our next live session, and I hope you have a great day.